This is an AP chemistry video. This is going to be covering, it's an addition to the notes and video that I already have on 3.4, the ideal gas law. I wanted to do a few problems that are similar to some of the web assign questions. So in this question, we have a gram of hydrogen and a gram of helium in a 1 liter container at 27 Celsius. And we want to calculate the partial pressure of each gas. There's more than one way to do this, but what I am going to do is actually use the ideal gas law for each one of the two gases. So I am going to take my grams of hydrogen and calculate my moles. When I do that, I get 0.495 moles of hydrogen. Similarly, I will do that with the helium. So 1 gram of helium, molar mass of helium is about 4. And when I do that, I get 0.25 moles of helium. So then I know the volume of the container. So the volume of the container, so now I know N. So here I have N is 0.495. The volume of the container is 1 liter. The temperature is 27, which is, if I add 273.15, that would be 300.15 Kelvin. I know R. And then I can solve for pressure. So pressure times the volume is going to equal the moles times R and that's liters atmosphere over Kelvin mole, and then multiplying by the temperature, 300.15 Kelvin, and then I would divide both sides by that volume. And then you can see, by the way, that the units all cancel. I'll show you. So the liters cancel, Kelvin cancel, moles cancel, and I'm left with atmosphere, which is good because I'm solving for pressure. So the pressure of, and this was the partial pressure of the hydrogen, is going to be 12.2 ATMs. So similar, I am going to do that for the helium. So I'm going to move this a little bit, make it a little smaller, switch to a different color so that you know I have switched over, and now I'm going to do pressure of the helium times volume of the container equals the moles of the helium times R times T. So the pressure of the helium times the 1 liter container equals the moles of the helium. There's another sig fig there, by the way, times R times temp. Divide both sides by 1. And then I should get the pressure of the helium as being 6.16 ATM. So those are the partial pressures of each of those two gases. Let me show you another problem. This one is, if you are given an empirical formula, you can calculate the molecular formula fairly easily in this question. So we are considering that there's a 256 milliliter flask at 373 Kelvin, 750 torr, and it contains 0.800 grams of a gas. And we know that the empirical formula of the gas is CHCl. So I'm just going to set myself up here. I have the volume is 256 mils which is 0.256 liter. I have the temperature already in Kelvin. I have the pressure in torr, and I know that there's 1 ATM for every 760 torr. So that means my pressure is 0.987 ATMs. And then I have my mass of my substance. So I am going to use the ideal gas law, and I'm going to substitute in, and this is on your formula sheet, moles equal mass divided by molar mass. So I'm going to sub that in. So I would get PV equals little mRT over big M. And what I'm going to do then is I'm going to solve for big M, which is my molar mass. So big M, and you can put your numbers in first, but I am going to do it with variables first. So now I'm just going to plug in my 0.8 gram, my R, my temp, and then over my pressure and my volume. So when I do this, I get a molar mass of 96.91 grams per mole. The unit of my R, remember, is liters atmosphere over Kelvin mole. So I can see that my Kelvin cancel, my atmospheres cancel, my liters cancel, and I'm left with gram per mole, which is good news because we're solving for molar mass. So now, if I know that that's the molar mass of the molecule, then I can determine the molecular formula by taking this and dividing by the empirical molar mass. So the empirical formula was given is CHCl, and the molar mass of that is 48.47 grams per mole. So I'm trying to figure out the ratio of the molecular molar mass to the empirical molar mass. So I'm going to take my 96.91 over the 48.47. They're both in gram per mole. And when I do that, that gives me the multiplying factor. I call it N, but it can be a little confusing because that's not mole this time. But it is the multiplying factor for taking the empirical formula to the molecular. And we hope for whole numbers here. In this case, I think it's like 1.9999. So essentially it's 2. So that means my molecular formula is going to be C2H2Cl2. And that is all I have.